Through instrumentalizing natural processes of evolution and growth within a computational framework, we can begin to model essential features of emergence that have impacted and influenced an organism's final form. This project focuses on designing a methodology for a reactive architecture, whereby initially investigating core principles of growth, the logic of an adaptable design was formalized. Through responding to a variance in local climates, this project proposes a design that is both directly informed by its surroundings and adaptable to them.
By researching core principles that define the growth and form of a snapdragon flower, this led to applying the varying logic of its growth through a rule set to guide and influence a methodology of simulating the growth of the flower. Research conducted by John Innes at the Norwich Department of Cell Development Biology discovered that altering the location and rate of growth along a surface, a sheet can vary between a ball growth to an edge curl growth. This basic logic can then be transferred into a modeling technique, or phase, through establishing a list of rules that mimic the form and appearance of the flower. In this particular case, growth is enabled through the application of direction and multiplication. This sequence is repeated with incremental levels of control to allow for a form to continuously evolve and grow. By altering the original birth geometry, followed by applying the logic of growth, which is corner selection, curling, and then repeated. In this particular case, only 3 stages of growth are simulated. The complexity observed in the simulation is a byproduct of simultaneously running all the stages of growth together from the beginning. Through rigging the process of growth procedurally, with the parameters defined and the language of the flower embedded through those parameters, the simulation of growth and the process can then be run simultaneously to create any number of variations of the form through altering the parameters. Essentially, all the surfaces are grown inclusively rather than incrementally. All parts of the surface are modified during the process of growth. When paused during this sequence of digital growth, we end up with a form built from the given parameters and language, but not necessarily the anticipated final form. The subsequent logic and language developed through this process of growth can then be applied in a proposed language of a building, whereby through the production of these unanticipated forms, the logic is interpreted into a performative function, where principles of growth and transformation are taken forward. The use of inflatable surfaces could be speculated to drastically alter our physical space, where through varying levels of inflation or growth, an alternative physical condition is created, one that could provide varying levels of shelter from our surroundings. These deployable surfaces are then speculated through tactical positioning to provide a controllable degree of deployment. This could both alter one's physical environment but also respond to elements such as motion to trigger its inflation. This use of inflation can then be questioned as to the material qualities that these surfaces can provide. The non-static feature of inflatables allows for a reactive interaction with said surface. This interaction could be displayed through a physical space being altered by its inflation, further manipulated when triggered from the motion of the occupant, changing the purpose of a space based on a user's needs. Effectively, this could then develop into a fully reactive form of architecture, where our immediate environment becomes a reaction of our actions, and subsequently these triggered reactions could completely alter the occupied space the user inhabits. This transformable property could then apply to household objects, such as a chair, where its function is activated on command through additional inflation. The chair can further alter its function so as to provide the additional feature of shelter. To enable the particular bending motion of said panels, simulations were run in fabric testing software Marvelous. Through a series of tests, the proportion and degree of bending can be determined through the placement and angle of air pockets placed along a surface. To achieve more complex forms, the inflation principles developed were combined with complex seams to articulate and control the inflation of the surfaces. By varying the air pressure between the layers, the growth and shape is subsequently varied.
The inflatable tests were then translated at an architectural scale, whereby the facade becomes responsive to its environment through either acting as a non-kinematic ventilation system or solar mediation through surface alteration.